Okay, so we are in search of quartz. What do you think? Am I gonna find any here? None in that pocket. Nothing up my sleeve. Probably not quartz, huh? Probably not. What do you think? Might be quartz, huh? Might be. Let's count the sides. 1, 2, 3, 4, 5. Whoops. Might be 6. Might be 6. But hexagonal, the definition of the hexagonal system is that it is two perpendicular axes, even perpendicular axes, and one either long axis or one short axis. And you'll see some of that in my rubies and sapphire, little short tabular crystals. Um, Tabular is this one got cut in a octagon, but tabular means it's flat like a tablet. Okay. So and this has 6 sides, but it is not in fact hexagonal at all. Having 6 sides does not mean that it is forming in the hexagonal system. Okay. And quartz would, if I could actually find any, and I can't, um, would have bond angles that are associated with the way that the oxygen collects around the silicate atoms, um, silicon atoms. Silicon has 4 electrons in the outer valence orbit, the ones that join up with other things. Um, and silicon dioxide is said to be hexagonal, um, and the chemistry doesn't actually work for crystals. I'm sorry, it doesn't. It doesn't. You can't have 4 oxygens around a single silicon atom. Um, you gotta have at least 6, okay, to start with. Um, and then 3 on the top and 3 on the bottom. And what you end up with is a cubic structure that has 3 even perpendicular axes. Let's see if we can find one here. Like that. Like that. and quartz, if it had bond angles between the 4 silicon atoms, it would be dividing up 90 degrees, right? Which is divided by times 4. Well, no, let's see. Times 1.6. Each one would be an increment, so 90 times 1.6 is 144. And that is, in fact, the calculated bond angle of quartz um, between the 4 the 4 oxygen atoms around the silicon atom. And can't form like that, you guys. But anyway, and it wouldn't form in 90-degree angles. It would only form in angles that are some, this is about 144 degrees. Okay, right there. And that would be, if you divide that up, 72 degrees or 36 degrees or what, 17 and a half degrees or whatever it is. I I don't do fractions, remember. But degrees are a little different, and we have circles that we can look at and mark where the degrees are and where these things form, and it tells us a little bit about the crystal structure inside the crystal lattice. So these angles are not random at all. They are a mathematical progression of the growth of this particular crystal of carbon. And carbon grows in the cubic hexagonal system, and it's cubic in one direction and 45 degrees out of phase. There are 6 sides, and that is because each carbon atom is surrounded by 6 other carbon atoms. They're all the same size. And that's as close as you can fit 6 little spherical objects together on a plane. And then there's 3 on the top. And what it does is it creates spaces for 3 more things. 1, 2, 3 on the top, and 3 on the bottom, and the next thing you know, you've got 13 atoms in a unit cell. And the unit cell of carbon determines what colors we see in the crystal. And in this case, there's some kind of reddish, maybe something reddish, like rusty, like maybe gold, in the planes of cleavage. Between, not in the crystal itself, but kind of pasted on the outside. I think that's what that is anyway. I'm not sure. But the crystals are not red, they're clear. And the planes of cleavage in a red or a blue or a green diamond are half the size of that particular shade of whatever color it is, because the light bounces inside a clear crystal, but it bounces at half the size of a wavelength of light. So if it bounces from the top to the bottom and back up to the top, it's a whole wavelength of light. Boom, boom. And that is why diamonds have colors associated with the depth of formation. Okay, and they can form in the cubic system as cubes, or this way, long ways, but the crystals aren't like hexagonal. They're not. They just have 6 sides. And they're primarily cubic. Which is why you get all these crazy shapes and stuff stuck together, but if you look, they make 90-degree angles and stuff. And like this 144 degrees is actually just like an extension, but it was this and this, right? And it's actually part of a 90-degree angle. Look at that. And it's a 45-degree angle from that 90-degree angle. Oh, wow, huh? And you can measure it with, a little simple trigonometry. Bump, bump, bump. See? Isn't that cool? Yeah, that's fucking cool, man. And they have 90-degree angles. See the 90-degree angle here? It looks like a pyramid, kind of. Oh boy, making those little things all the. And now you know why they're all stuck together like that, because they were actually floating in liquid rock, right? Molten metal. The semi-molten metal was moving towards the surface of the Earth. And when it hit the 3,800 degree Celsius mark, and it's got some AUPT dust on it, so ignore that, please. Um, anyway, when it hit the 3,800 degree and cooled below that, the carbon begins to crystallize out. And it starts as a little tiny thing, and it gets bigger and bigger and bigger, and then it grows according to how much stuff is in the liquid right around it. And it continues to grow as long as there is carbon in that liquid, until it cools beyond a certain point. And beyond that point, and look at this. Look at this. There's a kind of a flat spot there. That's the growth phase of another crystal. And they just kind of grow together as it moves upwards. And those intergrowths are because they're actually one crystal. It's not a whole bunch of little crystals stuck together. It's just one. And, despite me talking all this time, some of you are saying, well, that's fucking quartz, man. I know what quartz looks like. Okay, so what you do is you take a laser pointer, 3 different laser pointers, okay, blue, red, and green, and shine them at this one at a time. This kind of clear quartz stuff that you guys call quartz, and it will fluoresce in all 3 colors because it has carbon-14 in it that gives off electrons at the same wavelength as the light that's exciting it. Okay, so I get rainbows in white light. Okay. But this will fluoresce in any wavelength because of the carbon-14. It's not red, it's not yellow, it's clear. There's some radiation coming off of it that's reddish. It may be beta emissions from um, PT-190, platinum 190. It's the radioactive isotope of platinum. Very common, and one of the most common constituents of the radioactive volcanic ash, this stuff, this white stuff that covers the earth. So, and these things are found in that radioactive volcanic ash, and pockets in igneous rock that cools deep underground in fault lines, in the basement rock that makes up the entire crust of the planet. And if this was the center of the planet and this was the crust here, the crust would be thinner than this white powder on the surface. That's how thin the crust of the planet is compared to the planet itself. So, and everything underneath of the crust is semi-molten, or way down in the center is smooshed together so much it's solid. And so the outside travels at a little different rate of travel than the inside does, and that creates that electromagnetic field that prevents charged particles from the sun from landing on living things on planet Earth. And part of it is because this stuff here is listed as prosite in Wikipedia, and you'll find a picture of some purpley stuff that has a similar crystal structure to this in Wikipedia. They say it's the most common mineral on the face of the earth, and it is. It's carbon, just like you and me.